Hello. Yeah. Hi. I'm happy that you're here, and I'm going to talk about cellular automata. Just let's check out who of you knows Game of Life. Okay, we can work with this. So, what can you expect from today? First of all, I'll give you some introduction to cellular automata, the formal model. Then I want to give you a demo of the software that I want to present, evocell. Many different cellular automata and how to play around with them and mutate them, evolve them. Then I want to talk about artificial life in cellular automata, automata, I've been told, sorry. Yeah, and then I will sum up what we've heard. So, what is a cellular automata? It was introduced by von Neumann and Stanislav Ulam in the 40s, I think. So the father of our computers is also the father of cellular automata. And at this URL, you can find a very interesting paper from that time, if you're interested. It's a mathematical model for a dynamical system that is discrete in time and discrete in space. You will see what this means later. And the dynamical system, it depends only on local interactions. But the interesting thing is that global phenomena emerge out of this local interaction. So, the elements of a cellular automata. Yeah, some regular lattice of cells. It could be a different lattice, but it has to be regular. And at each of these discrete time steps, each cell is in one of S different states. And of course, normally we code the colors, we code the states with colors so that it's easier to visualize. And then the state of each cell at time step t plus 1 is a function of some of its surrounding cells at the previous time step. So yeah, imagine it like this. The sum of the neighboring cells, they influence what the state of the center cell will be in the next time step. And each cell has the same relative neighborhood, so the same neighboring cells. And normally the center cell also influences which state it will have in the next state. So the center cell is also in the neighborhood. This could be confusing otherwise. Because normally you wouldn't think of the center cell as a neighbor of itself. Yeah, typical neighborhoods we will see the von Neumann neighborhood that was used in the first cellular automata that he introduced in the 40s. And then the Moore neighborhood you all know from Game of Life. Yeah, but we could also make the neighborhood bigger so that more cells influence the state at the next time step. Yeah, and how is this influence really modeled? Think about it. For each possible combination of states in the neighboring cells, you have one target cell that the center cell target states the center cell develops into. And this is simply implemented as a lookup table. An example, let's take the Moore neighborhood with 3 states. Then for each possible neighborhood, we have one target. We have one target state. Yeah, this summarizes what I've said so far. And now we can we can ask ourselves the question, how many different cellular automata exist that are like this? And we just, this is a problem. We can just split it in 2 parts. And First, let's ask us how many different neighborhoods do exist. And yeah, each of the n cells in the neighborhood can be in one of S states. Here's an example. So this can be in one of S states, this can be in one of S states, and this two, and this two, and this two. So there are S times S times S, S to the nth power, different neighborhoods. It's analogous to numbering systems with the base S. So it's easy to calculate. So for each of these S to the nth power neighborhood, we have to assign one target state. So if everything is 0, we have to assign one target state. If the center cell is 1 and everything else is 0, or if it's 2. And for each combination till every state is S minus 1. We have to assign one of S target states. So completely analogous to how we calculated the numbers of neighborhoods, we get there are S to the nth power different possible cellular automata. And this is a huge number. And the question is, how do we find the interesting cellular automata in this huge space of possible cellular automata? Here's an idea. We could evolve them. This is an algorithm I would propose. We start with some initial rule, and then we make some copies of this initial rule and just change some entries in the transition function table that I've talked about before. And then we initialize the original cellular automata and the mutated cellular automata with some predefined or random cell pattern, but each with the same cell pattern. Because then differences in the transition function will be seen as differences in the development of the cell pattern. I will demonstrate it shortly. And then we just select the most interesting CA and go back to the start. This can be iterated, of course. And before I show you the demo, I want to talk about symmetries, because if you think about this transition function, then yeah, for example, if I have in the lookup table, I have this entry. So when in the top left corner there's a 0, everything is 0, and these states 1, 2, 3, then I want the center cell to be a 2 in the next time step. Normally, in game of life, for example, the transition function is symmetric. That means if I have this entry, I will also have these entries. These are just the rotated versions of the same, rotated by 90 degrees each. Usually the rules I will show you will have this property. They are symmetric. And the interesting part about the symmetric rule, if you start with a symmetric pattern and you have a symmetric rule, it will always stay symmetric over time. And this is rotational symmetry. You can have the same with mirror symmetry, for example. So this would be the mirrored version of the same transition rule. Okay, let's have a look at this in action. Yeah, perfect. So you see the cells here, and to start with, I thought about we just take some patterns you might already know. And you know, Conway, the inventor of Game of Life, he had to simulate the cellular automata on a Go board. And John von Neumann, he couldn't even simulate it on a Go board, he just mathematically proved that it would work. But today, of course, the computer calculates it for us. So Let's have a look at it. Yeah, it's the glider we all know from Game of Life. Most of the time I don't want to draw the pattern myself, I just want some random cell chunk that I want to see how it evolves. So this can be done easily, like this. So, but I promised you new cell automata, not the old ones you already know. So let's create something new. First of all, I have to define a neighborhood, of course. I have to tell him which cells influence the next state. I'll start with the traditional Moore neighborhood. So this is the center cell, and all these cells influence it. And I start with 4 states, as you can see here. I create this. Now I have it here. So what happens if I'll switch to another color scheme so you can see it better. Oh, it's bad. Okay. So I just initialize it with some random pattern, and what happens if I now calculate one time step? Everything goes to 0, because in the beginning each neighborhood goes to 0. I have to change some rules. How do you do that? Select it. Here, this is now again a picture of the neighborhood, and this is similar to regular expressions, really. All these question marks mean I don't care what state is here and here and here and here, but I want the center cell to develop into, for example, n0 minus 1. n0 means is the zeroth neighbor. This is this one. n1 is this, n2, n3. So these are the neighbors. And I just say, I don't care what the neighborhood looks like. I just want the center cell to develop into the state it was before, minus 1. So it will decrease in the state. And when it's 0, it doesn't switch to minus 1 because this is not a well-defined state. It stays at 0. And I want to change all the rules that match to this pattern. I could also just change, for example, 500 rules that match this pattern. But I want to change all the rules that matches. And now I mutate it, and let's initialize it, and step. Yeah, everything decreases one state, as I told it to be, of course. Now this is a more interesting rule, but it's still rather boring. So let's make more cell automata. Just well, and now I have 4 of them, and this one is the first. This still has the rule I just initialized. And now just let's do some mutation. But I don't want to mutate it randomly. I want to mutate only specific rules. Rules that match this pattern. Well, so I only want to mutate rules that have zeros here, and I don't care what's down here or here or here, but I want the center cell to develop into the third neighbor. The third neighbor, it's this one here. So this one, it grows out. And let's say I want to mutate 20 entries in the rule table, and I want to have rotational symmetry because it just looks nicer like this. Okay, let's mutate it. Let's look at how it develops. Oh, interesting. Because, of course, the rules that I've defined here, zeros here and any state here, they match for here on the border